hardware architect at Azure right now, and of course, a professor emeritus at the University of Wisconsin-Madison. Every one of us has read many papers of Mark, so we're really excited to be here. He wants the talk to be interactive, so please ask questions. Yeah, we'll do our best to, and I'll give the stage to you.
Okay, thank you. All right, so the title of this talk is In Computer Architecture, We Don't Change the Questions, We Change the Answers. I will explain that. So, you know, first of all, architects take components like steel and concrete, and they build systems for different purposes, be they celebrating technology or celebrating spouses. Computer architects, you know, borrowed this metaphor because we do a similar thing in taking components and build systems. The difference is that we do it sort of hierarchically, right? There's gates that produce ALUs, and then functional blocks, and then cores, systems on a chip, servers, and data centers. But the sort of principles remain the same. We're going to connect things together and hide complexity.
How are we celebrating our spouses?
That's the Taj Mahal.
No, we as computer architects.
Oh, well, I have not built my wife a Taj Mahal, and I don't think she needs to know that Taj Mahal was built honoring a spouse.
I think the Apple Lisa is pretty close.
And what's that?
The Apple Lisa computer.
Was that spouse or daughter?
It's daughter, but yeah.
There you go. Anyway, so since December 2020, I've been working for Azure. So this is my system. I have this absurd picture to make people remember that I treat a data center as a computer. And what I'm doing is sort of hardware, software pathfinding, which you can think of that as sort of a step in from research. One end of the path could do research, but also you know, could just take other people's research. And then, but I have to pay attention to the other end of the path, which is the Azure plan of record, and to try to get some of the things sort of really affecting this system. And what's exciting about it is there's lots of power, and Azure's motto is building the world's computer. The hard part is we're sufficiently successful that sometimes there's resistance to change. Okay, so one of the reasons I joined Azure, and I think computing is very exciting now, is that we've had this stack for a long time where we've divided and conquered complexity problems in applications, middleware, runtimes, across the hardware boundary to microarchitecture, hardware, materials, and fabrication. And in the late 20th century, things were moving so fast because Moore's law was working so well that everybody had to stay in their lane, in their layer, because there was so much change. The interfaces were relatively fixed to divide and conquer the complexity, and you didn't really need to cross because there was so much happening. With the slowing of, you know, and by the way, I should point that the reason this New Yorker thing is here is to show people, everybody thinks their layer is most important, and I do as well. But we need to cross layers because with technology scaling slowly, you're not going to get humongous gains completely within a layer. And like I said, I think this is the challenge for computing in general. And you know, the reason I joined the cloud service provider was that we have a lot of this in-house. Okay, so the structure of this talk comes from when I was a brand new professor. I asked a senior colleague, how do we update the questions on the computer architecture PhD qualifying exam? And Jim Goodman answered, Mark, we don't change the questions, we change the answers. Now, this was a flippant response, but 30 years later, I realized there's a lot of truth into that. To a large extent, we don't change the questions, but it's the application use cases above us and the technology innovations below us that change the answers. And then it's our job to recognize those changes. So this talk is going to talk about some of those changes and some of the possibilities of what you might do. So it really has more questions than it has answers. And the goal is, I hope one or two of you, walk away from this talk with a, well, I could work on that idea. Okay, so what are these questions? how best to do these interacting factors, compute, memory, storage, interconnect or networking, security, power, cooling, and then I'll have a bonus new question at the end. And I'll spend a little bit time more on compute and memory, partially because that's closer to my skill set. All right, so what's happening in compute? You know, if you've taken enough courses, this is not new to you. Accelerators are really expanding. You know, let's just define them to be clear. It's a hardware component that executes a target computation class faster and usually with much less energy. It's actually the much less energy that's often more important, because once you go through the overhead of getting to the accelerator, it may not be faster. But since we're so energy limited, if you can save a lot of energy, you know, it's not that you, usually it means you can do more, you can do other things. So a place where it's really taking off is deep neural networks. This is the TPU from a few years ago. This is the Synchronous wafer scale engine, which I don't know if you're familiar with, but the idea there is they take a wafer and instead of dicing it up into chips, they package the whole wafer with some redundancy and use that to accelerate deep neural networks. And then I put the human neocortex over there to remind us that a human brain can still do some things that we don't do in computing, and it does things with 3 or 4 more orders of magnitude more energy efficient. So you can't say we've tapped out the possibilities.
This is maybe a flippant question backwards is, are we on a Moore's law for energy reduction because of accelerators? Like, are we going to get there in 3 or 4 generations because we're, you know, every, say, n years, we're reducing the power of computation by half, or are we still on a linear trajectory towards the human brain?
So I don't, you know, well, so for Moore's law in some sense had 2 phases.
Yeah.
One is sort of Dennard scaling, was sort of just working. And then there was another 10 years of sort of one-off tricks that gave the appearance of a smooth going forward. I think with energy reduction, we at best have one-off tricks, but I don't even think we have necessarily a roadmap of one-off tricks. So I don't see us on that trajectory. You know, to get anywhere near the brain is going to require fundamental advances. I mean, it's not clear. I mean, analog circuitry, for example, may be needed in some cases, and you know how to make analog circuitry, you know, reliable and predictable enough is very hard. And we're going to have systems that are mixed, right? You know, we'll do some things that can be more analog and some things that can be more digital. I don't really know, but I don't think it's easy. But given we have no choice and engineers are pretty creative, I'm actually pretty bullish, because in the Moore's law phase, I mean, basically the deal was, congratulations, you've designed an optimal processor. Now your budget of transistors has doubled. That old design is not optimal. Do something for your new budget. And in this new era, we're just going to have to look creatively for opportunities and waste. Yep.
What do you think changes faster, the technology or the applications? One, it's hard to think of a new application like besides machine learning. I mean, there will be changes and tweaks to ML and neural networks. But
so the greater changes are absolutely coming from the applications and use cases. And you're exactly right. It's really hard to predict. I mean, you may remember 15, 20 years ago, people were saying, we don't need faster computers. You know, Word runs fast enough, right? And I guess I'm fully, and I have another talk that has a bunch of these use cases, but I mean, I do think, you know, virtual reality and augmented reality, you know, it's like overhyped if you listen to Mark Zuckerberg, but I think it's really real. Self-driving cars, the general case is very difficult, but there's sort of a lot of useful cases, you know. In 20 years, you know, I'll be happy that a self-driving car can take me to, you know, local stores and a doctor's office, even if it can't drive, you know, up to the Sierra Mountains in the worst conditions. personalized education where, like, as an instructor, you're always trying to find the examples that, stretch your students, but don't break your students. And that's student dependent. I don't know what those applications are, but I just gotta believe that if we can make computing more cost effective, it will be, the use of computing will actually expand. It's not a case that we make it more cost effective, so, the people doing computing shrinks because it's so more efficient. But it's really hard to predict. So an example with accelerators really working well, right? Almost anybody can go in and design the kernel of an accelerator to do this, that, or the other thing. But what really matters is whether it works end to end in the system, and often that requires co-design. So we'll give an example on the arithmetic formats for inference. Originally, inference was done with 32-bit floating point, which has a red sign, a green exponent, and a blue mantissa. We then moved to doing it with 16-bit floating point. Google had this innovation. Instead of using IEEE 16-bit floating point, it uses the one in the box there, bfloat 16, which uses the same sign and exponent as the 32-bit. This has two advantages. One is it had greater range, which turned out to be more important than the precision in the mantissa. And secondly, it makes conversion between 32 and 64-bit really easy because you just lop off some bits or add some zeros. But how do you go further? An example of going further is Microsoft floating point. And this takes an old idea called block floating point. And what you do is you share the exponent among some number of numbers. And then if you do the calculation, this example shown here is using 4.5 bits per value. And if you do that, it doesn't work. It doesn't work until you do some co-design and make sure that the neural network works in such a way that the dynamicism within that block is small enough that the shared exponent, captures it. And that's a good example, I think, of the co-design that's going to be needed. Going forward and getting toward the human brain is we really need to exploit sparsity. I mean, the neurons in the human brain are very sparsely connected. And so that turns into essentially, sparse matrix vector multiply. And, how to do that best is a big challenge. And it's always been, you use unstructured sparsity, it's almost impossible to make the hardware work. And if you do structured sparsity, it requires co-design. So, this is just one example of the co-design that can happen in deep neural networks. And I think we're going to see a lot more. And by the way, my own opinion is that we're only at the beginning of the neural networks working, and we need advances in the science to make them, for example, have a world model so they don't say absurd things. I guess I'm being recorded, so ChatGPT is nice, but it's not everything. I think one of the exciting things is that because of the need for energy efficiency across a workflow, there's going to be many situations where we're going to deploy many accelerators. So instead of focusing on designing your one better accelerator, you can focus on designing many. This is an extreme example, an Apple chip from a few years ago, which has 2 big cores shown in the green big box and 4 little cores shown in the little box. And the rest of the chip is used for caches and various accelerators. I see this as this kind of design spreading to other situations. And if you think about it, what's happening is the CPUs are the control plane and the accelerators are becoming the data plane. But the CPUs, in my judgment, are never going to go away because there's always going to be stuff that in your workflow that you sort of didn't predict, and von Neumann computing is very good at it. And so I think there's a whole science that needs to be developed, and we have a paper, ACM Viewpoint, calling for this, of how best to, design these things and coordinate. Because, for somebody like Apple with literally 1 billion customers, you can just throw an army of programmers and make it work. But if you want to do sort of important things that have fewer customers, like you're designing high-end medical equipment, you need to have better abstractions to make this work.
What are some of the other 42 accelerators? The first hit on Google is your slide, actually. So.
Well, that's good. I like that. Should be using Bing, though.
Yeah.
There's a neural engine here. There's a GPU. There's some image processing accelerators. And I don't remember more than that.
Bitcoin, clearly.
Bitcoin, yeah. And going forward, there's going to be accelerators for data movement, for compression, decompression, encryption, and decryption. Because CPUs are like particularly bad, like compression and decompression and encryption and decompression. CPUs are bad.
So how do they integrate? Right, they put 42 accelerators on chip, but I look at this and I go, how the heck do they communicate?
Mm-hmm.
Well, that's exactly my point.
Yes.
They communicate in a very crude way. And they throw programmers at the problem. And many times they have to communicate through some shared memory, often off chip.
How are they even getting to that? Because
There's a whole bunch of buses, and I'm not an expert on this chip. I didn't design it.
Yeah.
But I just think going forward, that is exactly the right kind of questions. Like, do you have a scratch pad? Do you have a queue abstraction? What happens if you have to use an accelerator twice in your workflow? Can you virtualize it and have 2 half accelerators? I mean, I think there's lots of questions for making it sort of work better in an abstract way. Queues, I think, have a lot of promise, but you don't want to make them too rigid.
So I assume every accelerator has its own interface, and so it's very labor intensive to build these things, whereas when we had our nice stack, we had only a very limited number of interfaces that we had to implement, right? So how far can we go here? What's the trade-offs of basically punching through these layers and doing co-design versus just...
That's what I think academia should punch through it, because what's happening in industry is, you get the IP block from somebody and they have their own basically ISA and software development kit. And each of the accelerators is kind of like a silo. And there are times when, you have to go all the way back up the operating system drivers, to actually communicate. And it's just a total mess. I have a whole talk on this actually, but it's a little obsolete now. But I think doing this more elegantly is one of the big challenges facing computer science.
So I think with the co-design, does it involve more compilers, because it's more workload on the compilers to actually utilize all those accelerators? And
well, I mean, there is a question. I don't know if it's the compilers or it's the runtime systems, but we need better abstractions. I'm not a big believer in you just write this program and some compiler is going to map it to the 42 accelerators. I think that high-level partitioning, at least for the foreseeable future, is going to be done by humans. What we would like is then, as you program each of these accelerators and have them communicate, there's a relatively uniform environment. And to what extent is it hardware supported or not is open. I like the Vikram Adve and others at Illinois have this model, which I can't remember the name of it right now. But it models computation as a directed graph, and then within each node, you program the logic of the node. And so I can see something like that developing. I don't see you writing a single von Neumann program and relying on automatic parallelization into accelerators, because automatic parallelization for vectors is, 40 years old and medium successful.
So did you draw all the boxes on annotate this chip layout, or who?
No, that was I stole that from Tech Insights. I only did the 2 green squares. Yes.
So do you think if CPUs are going to be only the control plane, they should fundamentally change their architecture or design because most of your processing is going to be done by accelerators. There's a lot of things in a CPU that actually slow this thing down of like passing data.
So that's definitely possible. I see CPUs as A, being the control plane, and B, being the computational resource of last resort. And as things change, there's always some part of your workflow which you didn't like have a good accelerator for. And so how that changes the CPUs, I'm not going to speculate on. That's exercise for the students. But I do think it'll cause change. All right, so you guys have been, so we're supposed to finish by 11, right?
We can continue.
11:15.
All right, so another really interesting thing, which I'm kind of mixed about really, is processing in memory or processing near memory. It's an old idea. There's a 1995 paper, which is probably not even the earliest, but since computation is becoming more efficient, faster than communication, why not communicate way close to the memory where the data lives? Okay, and it's being revived by this energy problem. There are some deep learning and recommendation systems that work pretty well, and we're getting serious attention from memory vendors. There's a research paper out of Samsung which actually fabricated it. What's tricky about it is we really have to remember to co-design, because you can easily design this hardware, but it requires the use cases to have a small amount of compute that then goes with a large corpus. You can think of it as a search query goes to the data. And you can't just show that it works really well for this kernel, because you have to show that it works and has a significant benefit for the whole workflow, including the stages that come before and after the PIM. So I think it's an interesting thing, probably more applicable to more special purpose situations. And people always ask me, are we going to do this in Azure? It's like, Azure has to do a lot of things. We're not dominated by one application, so it won't happen in Azure first.
Do you not already do some of that? And like this processing memory specifically like on a chip, but don't you already move some of the computation to where the data is in Azure?
Oh, certainly. Yeah. I mean,
That's maybe data center.
we have global abstractions, but then we seek to exploit locality at many, many different levels. And, the extreme of processing memory, you're actually doing it on the DRAM or memory chip. And then there's variations, like you're doing it on the chip underneath the HBM stack, or you're doing it on a CXL memory controller, which I'll show you in a couple slides. And so, some of that will happen, but if you do work on it, make sure you think end to end, because it's PIM. If PIM fails, it'll be because of the software and the abstractions.
You mean fail again?
Fail again. Remember though, the idea of SIMD was like niche for all of the 20th century. And then boom, GPUs really made it take off, and where would we be without it? So sometimes it takes a while for ideas to gestate and have the technology and the use cases evolve enough that they become part of the answer. All right, you guys love computation. We spent a lot of time on it. Memory. So, one of the great innovations that let computing explode was the movement from ferrite core memory to DRAM in the 1970s, and memory has scaled very well for a long, long time. This chart is a little bit old now, but you'll see, over the last decade, the scaling and the price per bit has not done so well. This year, actually, memory prices have gone down a lot because of the threat of a global recession, but that's just a transitory thing. There's two problems. One is there's a triopoly of memory vendors, and so they have high margins, and you would think, well, okay, economic theory tells you that if you have high margins for a commodity, someone else is going to join. No one else is going to join because the barrier to entry is just crazy. And it's not just the triopoly, it's the fact that cost-effective DRAM is still two-dimensional, and two-dimensional scaling is just not doing well. Right? Most of our apparent progress in the future of Moore's Law is going to be 2.5D stacking and 3D stacking, which there are some 3D memory things, but they're just too expensive to use. So that's a good opportunity here. And this is serious in my judgment. 20 years ago, processor cores stopped getting faster as fast as we would like to use the resources that Moore's Law enabled. We went to multi-core, which was a gigantic shock to the programming system. This memory change, I think, is going to be a shock as well. Not quite on the same order of magnitude, but it's not clear we can make it transparent.
Just curious, why not do a stack like keep thinning and HBM stacks kind of thing?
HBM is unbelievably expensive for general purpose compute.
I'm saying that approach, not necessarily HBM interface.
That is an approach to take, right? Right now, there's 3D stacked DRAMs, so you can get higher capacity, and it uses through silicon vias to connect the chips, and they're thin to some extent. And basically, the bits cost twice as much. And twice as much is like unacceptable in most situations. There's some, like you're running a super high-end database that you can't build that big of a machine any other way, then you pay for it. Otherwise, it just doesn't work. One of the big shocks about going from academia to industry is that you have perfectly good ideas where the cost is not quite right, and they're not used because cost matters.
That's sort of the point of academia, right? So you look at things and eventually you're projecting into the future and saying.
Right. I think the point of academia, I agree with you, is to use your intuition to say that there is going to be a crossover in the future, and I'm going to do a work to study that crossover so that when it happens, there's a body that people can draw on, and you do not have to accurately predict the timing of that crossover. In fact, I did work on, multi-processor systems, way early in the 90s, and because I thought they were imminent, and they remained niche for a long time, but then they eventually showed up, and that's okay. Whereas in industry, wrong timing is wrong.
Sometimes it's bankruptcy.
Often with bankruptcy. Okay, so what are we going to do about it? Well, fortunately, there's an emerging standard called CXL, or Compute Express Link. And what this allows you to do, we got our processor over there in purple, the standard DDR memory in yellow, level 1, and then this CXL protocol. This is a CXL marketing slide, so it makes that bus really big. There's a protocol that you then talk to another chip from which you hang other media off of. For those of you old enough, that's kind of like a North Bridge. And so you get a 2-level memory, but more importantly, the second level of memory off this buffer chip is available for innovation without convincing Intel, AMD, or ARM to change their processor, because we've convinced them to add CXL. We don't have to convince them to add whatever things you want to do with the memory. So for example, that's one place you could do PIM, or it's really not PIM, it's processing near memory. So among the things that we find interesting are where you take the second level of memory and you actually make it a pool that's available to multiple hosts, not shown in this picture. And you rely on the fact that the peak use of any given host is higher than if you pool, you get a little bit of statistical averaging, so you can buy less memory. And so this is a way you can save money on memory by buying fewer bits, even though the bits themselves are not cheaper. And the other approach, which looks a lot more like this picture, is to just do extended memory. But that relies on there being a reason that the second level nets out cheaper. So one reason is that before you were building one of those super expensive systems with the 3D stacked DRAM, and now you can just do it all with regular DRAM. That's a net win. And there's also a bunch of new technologies coming along. 3D XPoint or Optane failed. These new technologies are looking interesting, but one of the paradoxes of technology is that most new technologies fail, but most old technologies are eventually replaced. So DRAM's ripe for having a successor because it's not scaling very well. And but maybe maybe people will figure out how to make it scale, or we'll see a successor. Yep.
That's still a one-time trick, right? The pooling. So it's not really addressing the scalability issue of
Right.
RAM.
The long term is having the new technologies, and we're tracking many technologies, under NDA. And they're super interesting and technically work, but whether they become economically feasible remains to be seen. And if all of them fail and 3D, and there's also many attempts to do 3D DRAM, not just through silicon vias, but try to do it monolithic 3D. That will be a big limit to computing if we don't get past that some way. All right, you guys are excellent. I'm going to do this really fast. I just want to point out that if you're going to use this two-tier memory, you really do have to change the software often to make it work really well. So databases have something called a buffer pool, which is basically a hardware cache, a software cache of what's on permanent storage. And traditionally for a multi-core system or a multi-processor system before, most of the green memory would be just used for this buffer pool. When NUMA came along, the designers of the databases sharded the buffer pool so the core or processor used its shard more than the other parts. And for with extended memory or pooled memory, you have the situation where a lot of the memory is going to be next to 0 cores. So we call that 0 core NUMA or Z-NUMA, and that'll require restructuring essentially for the software cache mimicking a 2-level cache. And databases can do that. A lot of other applications that might prove more challenging. I'm going to skip this in the interest of time. There's storage is pretty interesting. And what's really weakness in storage right now is there's only 2 tape vendors and 1 supplier of some of the components. And so we need better ways for archival storage, especially since the amount that people want to save is exploding. Microsoft has a couple of research projects, but they're still out there. All right, data center networking. So even though in the data center, we tend to use Ethernet for most of our intra data center networking, because I look at this as a computer, this is my interconnect. It's not really a network just because it happens to be Ethernet. Okay, and the standard design these days is a folded CLO or fat tree. But we want to basically stick with Ethernet because it's very cost effective. But what can we do within that constraint to make it closer to a high performance interconnect? Now there's existing proof that you can do a lot better in bandwidth latency and jitter. InfiniBand is a specialized thing. It uses some Ethernet physicals, and Cray HPC Slingshot actually builds and is Ethernet compatible and can do much better. The problem with both of these is that they're single vendor solutions, and Microsoft doesn't want any of its suppliers to be single vendor. We just want to be your single vendor, right? All companies want that for higher margins. So what do we do about it? And I think you're going to see an industry consortium announced pretty soon in that direction. Another exciting thing from a technology point of view is that optics is moving closer to the server. There was a time when optics was more efficient than electrical, only like for transatlantic cables, and it keeps moving closer. So right now, Basically, all of this stuff is optics, but still from the top of rack switch to the servers and everything within the servers is electrical. And there's already today replacing some of that internal stuff with optics, it would actually work better. Certainly to the top of rack switch, but even within the system, it actually would have better properties of less beachfront taken from the electrical signals and less energy. It's just a small problem of cost. So we don't do it yet, but I do think it's going to happen. And it also is going to allow you to do different things because optics lets you sort of go further than electrical does with good signal integrity. And so we may see a change in the topologies, and with changes in topologies, better protocols make a difference. So it's a very exciting thing. It's like a branch of networking, but it's different than long haul networking. Okay, security is something that computers have been playing catch up from the beginning, trying to stay ahead of the bad guys. Initially, I think we built systems assuming too much trust. In the cloud space right now, the situation is if you run on a cloud like Azure, we promise to protect your code and data from insider and outsider threats. We'll do our best. With confidential compute, the idea is to try to move this from a business promise to a cryptographically protected situation. Okay, and in a lot of ways, we sort of know how to do this. It's just, can we do it efficiently enough? But it's pretty complicated. You need a hardware root of trust. You need to attest that every component is what it says it is. Inter-chip communication is encrypted. Things are protected in memory and storage. They're stored encrypted. Really hard things are things like replay attacks, which I don't have time to go into. And this is excellent because this can expand markets, because the people who didn't trust the cloud enough to come to us with just a business promise will be open to it. But it's difficult. One thing I think is, here's a nice paper that goes over some of the big pictures. I guess you stop touching the screen. Huh? I know some of you work on open source hardware. We were just involved in a open source root of trust. If you're doing a root of trust, you'd like people to inspect it. If you're going to let people inspect it, why not work with multiple companies and sort of agree on one and have it be open source and let people inspect it? So that's something called Calyptra. I think they picked it so that I can never spell it right on first attempt. But it's a pretty, you can look it up. It's a pretty cool processor. It, for example, doesn't have any interrupts because of the concern that interrupts could be a vector to, perturb it. And certainly a denial of service. And then finally, as security keeps moving forward, there's homomorphic encryption, which you may have seen, which is the idea that in theory, you can actually compute many things on encrypted data, never unencrypted even to compute. This started out millions of times less effective than unencrypted computation, but there's been great progress. And accelerators for special cases you can find from even the last ISCA. Homomorphic encryption, though, is not Turing complete because you can't do data-dependent branches because you can't look at the data. And so that's a big limit. Yes?
Do you expect like accelerators to make homomorphic encryption more feasible in the future? Because like this right now, it's like incredibly slow, right? Like if you want to process 1 million elements, it'll take you like a month.
Yeah, I mean, Daniel Sanchez at MIT, for example, has one homomorphic encryption accelerator that was in ISCA, I think it was last year. So I think that'll be a big effort. It'll still be, it'll be a part of the computation for a long time, probably ever, because it's not Turing complete. But yeah, I mean, if you make it so that it's, let's say you make it a factor of 10 less efficient. Well, if the data is important enough, you'll use it. I mean, what's an example? Like for example, you're doing a sealed bid auction where you want to figure out who wins and you want nobody to be able to know what anybody bid except the winner. That may be worth being 10 times less efficient. And so I can really see this happening for part of the computation. Voting would be another example. Yep.
Sorry, I completely lost it. Carry on.
Come back.
Yep.
So it happens when you use DRAM and forget to refresh.
Yeah, my DRAM's under stress right now.
So power, I mean, this is obviously a first order thing with an aren't scaling, not operating. I think it's very exciting what's happening in the IoT and mobile space, Internet of Things in mobile space, where you try to save energy. Best time to save energy is, do nothing well. When you're idle, don't spend much power. I think another exciting thing is energy harvesting, where you body worn parts can get energy from just motion. It's exciting in that space. It's also quite interesting in the cloud space. What's interesting is it's not really our goal to save power in a data center. It's like, oh my God, how could that be? The problem is that we have to contract with a utility for a constant amount of power for like order 10 years. And so the question we ask actually flips itself on the head, and we ask, how can we use a constant amount of power most effectively? And so there's a bunch of cool ideas for that. And maybe even eventually, by the way, intermittent power makes it to the data center. Now here's a paper on this power capping idea. So which at the hand wave level is, well, you've promised a bunch of customers that they can run and they have a peak power that they could use. And you notice that they're not using their peak power. So you opportunistically put in some lower priority work to use that constant power to create more value. And then if the customers decide they want what they're entitled to, you have ways of suspending, moving or terminating the lower priority work. And so that's the kind of thing you need to do. So the flip side of power is cooling. Remember, cooling is hard. Humans did heating in prehistoric times, and they didn't really do cooling effectively until the beginning of the 20th century. With the poor scaling, air cooling is reaching its limit. So systems are moving to cold plate, where at least the hottest GPUs and CPUs have a hunk of metal with some holes that water runs through, and you can cool it. You still have fans for the rest. The question is, what happens when cold plate runs out? And one of the things we're exploring is immersion cooling. So watch carefully at the animation. See, it looks like it's boiling, and it is boiling. So this is an example of two-phase immersion cooling that is not water. Water would completely short the electronics and also boils at too hot of a temperature. So this is a fluoroinert, and it boils at 50 degrees C, which is great. And if you remember your chemistry, you have this liquid that's touching your hot component. It has a bunch of heat. The heat boils and creates a bubble, and there's two super beneficial things that happen. Number one, you absorb the heat of vaporization for the phase change from liquid to gas. And secondly, the bubble wants to rise. And so it takes the heat away, without the need of a propeller. So it's very cool, literally. It also could interact with other questions in interesting ways. It keeps the temperature more constant. Will the components last longer? You have great incentive to move the components closer because liquid is expensive. You also have opportunity to move them closer because you're cooling them so well. But there are challenges with the fluids, both in cost and in environmental impact. So
how much power do you spend for the immersion cooling? And how does it come up with the actual computational power?
I don't know the number of that. There's a blog post, which is probably all that can be sort of formally said, but I don't think that's the limiting problem. The problem is, sort of the cost of the tanks and the And the other thing I didn't mention was obviously you're not going to want to sort of go in and remove an SSD all the time. So you have to think about sort of fail in place. So you don't have to, you can go in once in a while, but you wouldn't want to go in for each failed component. So there's a lot of interacting factors.
We play a little on the coolant. The problem on those ones, many of them were quite toxic.
That's right.
So you don't want to have it in your lab.
Right. So we now have some fluids that are not toxic, but they it's not clear. Environmental impact is still open.
Yeah, at the end we did mineral oil, but it doesn't have the oily property.
I'm not a chemist, so I don't know. There's also one-phase cooling where you don't get the bubble effect, but
They also have the active cooling, actually putting a thermocouple on top to extract heat away.
That's very inefficient.
Well, but they have constant power,
yeah.
right?
Well,
So,
you know, I don't. We're gonna. I mean, air cooling is gonna run out of. We already have the case, by the way, that we can't fully populate our racks, right? We leave slots empty in order to get, you know, enough airflow and enough power. So make improvements here, it can make a big difference. All
So
right.
yeah, even if you can dissipate infinite heat from the chip, it needs to go somewhere, right? So the boiling of this liquid will produce heat that needs to be.
Yeah, there's a secondary heat exchanger because you have to condense the bubbles. I mean, cooling is an unnatural act, right? That's why, you know, air conditioning wasn't invented until the 20th century. All right, so I said that in computer architecture, we don't change the questions. That's a model. My favorite quotes is George Bach said, all models are wrong, some are useful. I think it's a useful model, but there's a new bonus question that wasn't there when I was a grad student, which is how do we make computing more sustainable? And so one aspect of sustainability is greenhouse gases, which the US Environmental Protection Agency classifies in 3 scopes. So scope 1 is direct emissions. So if we run some diesel generators as a backup, that's on us, scope 1. We don't do that very much, fortunately. Scope 2 is emissions done by somebody else to make your business run. So if we got power for our data center from a coal-fired electricity plant, that would be a lot of scope 2 emissions. Fortunately, we don't do that. Cloud data centers in general are greener than most other on-premise data centers. And then finally, there's scope 3 emissions, which is basically your suppliers and your customers, right? Well, the customers not so significant for Azure, but it would matter for like Microsoft, Xbox, and Surface, what happens when they dispose of things. But for us, what's quite relevant is the suppliers. The number 1 cause of scope 3 emissions, anyone want to guess?
Silicon fabrication.
Silicon fabrication. Turns out it's done mostly in a part of the world which has terribly ungreen power as well.
Arizona?
No, mostly Taiwan. Very small plant in Arizona. And so scope 3 emissions are something that we're worrying about. What I like, I mean, and from a company's point of view, these scope 3 emissions, these scopes are a pain. What you'd like to do is outsource everything and say, hey, I have no scope 1 emissions. But EPA was smart enough to not let you do that. You get charged for all 3 of these. And so we have a big push to try to reduce our emissions. And Microsoft's not alone, but we're promising to be carbon negative by 2030, which means we're going to do some stuff to put carbon back in excess of what we're putting in, which to me is a pretty aggressive goal. I wish I knew how we were going to do that. We have some ideas, but carbon negative is pretty aggressive, but there is no planet B.
This just focuses on emissions, right?
Yeah.
But we just had talked previously about how there's fluorinated.
Yep. No, this is a single slide focusing on one part, right? There's the fluorinated, there's water, There's land use, there's many things. I'm not an expert on. By the way, in the architecture space, there's a really nice paper from Harvard and Facebook looking at some of these questions and spawn some later work and showing how things are different depending on whether you're battery powered or whether you're plugged in. But I think this is, it's an important question going forward, which was not really a 20th century computer architecture question.
So running TSMC factories on renewable energy seems a relatively easy problem to fix, right? So if the data center guys can do it, why can't they? It doesn't even seem that expensive.
I don't know. It depends which renewable energy you're looking for. I mean, I don't know. The nice thing about the scope stuff, right, is it gives customers at many different levels. We are a customer of fabrication leverage, saying we care about these scope emissions, do something. And so it turns a company doing something from being sort of benevolent act on the part of the planet to meeting one of your customers' checkboxes. So reducing the power is one thing, but there is tons of nasty chemicals in chips too. So I mean, that's beyond the greenhouse gases. Mm. The other thing, by the way, I don't want to let us totally off the hook. I mean, we can do things too. So the pooling memory, by the way, actually helps our greenhouse emissions as well, or our scope 3 emissions, because we buy less DRAM if we would do it. It's just a research project now. Can we run our parts longer? Can we do the same amount of work with fewer parts? Or well, we wouldn't do that. We would buy the same amount of parts and do more work. But those are things within our control. And so, and what's nice about some of these things is it's not everything you do here costs more. There are some things where you can make a green change and it's actually good for your bottom line as well. And this focuses your attention on those. The classic example for the general public is replacing an incandescent light bulb with an LED. Both saves you money and is more green. All right, you're looking at your watch, but it turns out I did well here.
Yeah.
So these are the questions that I covered: compute, memory, storage, interconnect, security, power, cooling, and sustainability. And I don't think they're interacting, and they can't be tackled individually, and they can't be tackled just at the computer architecture level, but we have to work with many others. And I don't know if my employers require me to put a commercial at the end, but we do hire people. Right now, there's like this bit of a threat of a recession, so hiring is largely paused, but that I expect will ease up at some point. So, thank you. So more questions? I mean, you guys are very active, which I